Lesson 2 talks more about functions. Remember, a function is kind of like a machine. Your body is like a machine. We input food and we get out energy. So there's other things that can be functions or machines. For example, it's a ruler formula that assigns to each input exactly one output. So equations are functions. If I input x, x is the input, I will get out y. So it's a function, it's a machine. Functions can be a table, a rule, a formula, an equation, a graph, a verbal description. There's all kinds of ways that functions can look. In exercise 1 through 5, let y be the distance traveled in time t. Use the function y equals 16t squared to calculate the distance the stone dropped for the given time t. A part of the notes that I left out talks about someone dropping a stone and figuring out the speed of it, which correlates. This is what it looks like right here. So if you were to time 0, you drop the stone. After the first second, it's going to go 16 feet. Now it's going to pick up speed as it goes. So after 2 seconds, it's gone 64 feet. After 3 seconds, 144. 4 seconds, 256. So you notice the farther or the longer it drops, the more distance it travels. To find the values for how far the stone fell, my function is 16 equals, or y equals 16t squared. So I'm going to plug in 0.5 for t for each one. So this is going to be 16 times 0.5 squared, which will give us 4. 16 times 1 squared, which is 16. And if I keep doing that, plugging in each different t value of time into this function, I will get the following numbers: 36, 64, 100, 144, 196, 256. So part A, so this is the table that was created in the notes part they left out. Are the distances you calculated equal to the table from lesson 1? It happens to be the exact same table. So yes, they are the same. Does the function y equals 16t squared accurately represent the distance the stone fell after a given time t? In other words, does the function assign to t the correct distance? Yes. Also, what I left out in the notes from the previous day, there's a graph that looks like this. Now, this is not a linear equation. Obviously, it's not a straight line. It goes something like this. This is actually, if you throw a ball, this is what it looks like. So it starts like where your arm releases the ball, you throw it in the air, and eventually it's going to come back down because of gravity and hit the ground. This is a function also. It's not a linear function, but it's still a function. And we're going to talk about more about how you tell if something's a function in a minute. So number 2, can the table below represent values of function? Explain. For every input, there can only be the same output. So for example, if the input is 1, I will get 7. So every time I put in 1, I should get a 7. If that doesn't happen, then this is not a function. So if you notice here, I have an input of 5 and an output of 19, and next to it, if I input 5 again, I get 20. That's not a function. Input of 5 has 2 outputs. Number 3, I'm looking for x values that repeat, which I have 2 of them right here. Now if this said 7, 15, 7, 15, that would be okay because it's the same output for 7, but this is not the same. It's a 15 and a 10. So this is not a function. Input of 7 has 2 outputs. Number 4, can the table below represent values of functions? If you notice, the 2 outputs are repeated, but not the inputs. 10, 20, 50, 75, 90. So there is no x value that repeats, so that's okay. It's possible that I could input 10 and get 32, and it's possible I could put in 20 and get 32, but I can't put in 10 twice and get 2 different values. So this is okay. Yes. Each input has only one output. This is just part of something that I added into the notes. Shown below is the table from example 2 of last lesson, another table of values. Make a conjecture about the differences between the 2 tables. What do you notice? Well, if I look here, each input has exactly one output. If I look over here, 1 is 4, 1 is 36, 3 is 99, 3 is 196. So really, this first table here, I can make predictions about it. Sorry, I can make predictions about it because for every input there's one output. For the second table, I can't really predict anything about it because sometimes for 1 second it goes 4 feet and sometimes for 1 second it goes 36 feet. Number 5, it takes Josephine 34 minutes to complete her math homework assignment of 10 problems. If we assume that she works at a constant rate, we can describe the situation using a function. Predict how many problems Josephine can complete in 25 minutes. So when I thought about this question, I said, okay, 34 minutes, 10 problems. She's working on it for 25 minutes though. How many problems would that be? So what I did is I kind of set up a proportion in my mind, and I looked at this and I found the unit rate. It's about 3 minutes per problem, so 25 minutes. So it's roughly 6 to 8 problems. Write the 2-variable linear equation that represents Josephine's constant rate of work. Well, in this question, we know we're dealing with minutes and we're dealing with problems. So I need to figure out what the dependent variable is, which is y. The number of problems she can complete depends on the time. So y is the problems, x is the time. So I'm going to write a ratio y over x. And I know already that she did 10 problems, 34 minutes. So that's got to be equal, because it's constant rate. So I cross multiply to solve this. 10x equals 34y. And I want y by itself. So I divide both sides by 34. Sorry, my cough is bad. So 10 over 34 reduces to 5/17x. So this is my linear function rule, if it's a constant rate, that I could use. So I'm going to use that equation to find part C, how many problems she would complete in 10 minutes. So 5/17 times my x value of 10 is 2.94. And if I plugged in 15, 5/17 times 15, I would get 4.41, and I keep doing that. 5.88 and 7.35. After 5 minutes, Josephine was able to complete 1.47 problems, which means she was able to complete one problem and then get about halfway through the next. Compare your prediction for part A to the number you found in the table above. So I guessed or predicted between 6 and 8. For 25 minutes, it was 7.35. So it was close to my prediction. Use the formula from part B to compute the number of problems completed when x equals -7. So I have y equals 5/17 x. I'm going to plug in -7 for x. So y equals 5/17 times -7. And I get y equals -2.06. Does your answer make sense? No. In this case, it does not. It would mean, in context of this problem, she completes -2.06 problems in -7 minutes, which obviously doesn't make sense. There's no such thing as -7 minutes. And -2 problems. For this problem, we assume that Josephine worked at a constant rate. Do you think that this is a reasonable assumption for this situation? In this case, it does not seem reasonable. It's kind of like when you're doing homework. Some questions are harder than others. Some questions might take you longer. So it does not seem reasonable to assume constant rate. Like I was saying, she might have done one problem, it's a tough one, in 20 minutes, then 9 problems in 14 minutes. That's a possibility. One tough question. So something like this, we cannot assume that it's a constant rate. Keep in mind the little box here, a function is a rule that assigns to each input exactly one output. So this is kind of like my machine. I input something and I get something out of it. Every input gives me the same output if it's a function.